All right. Our next speaker this afternoon is Alicia Lipscomb, who comes to us from Caltech. Alicia has been working with the other Alicia this summer and is going to tell us about their project together, verifying reliability of epoxy bonds for lens mounting. I'm going to pre-apologize to those who are joining us on Zoom, because I see that Alicia has brought along a lot of very interesting things that you are probably going to have more difficulty seeing, but it's going to be awesome for those of us in the room. So you can maybe join us after the break if you want to see them. So anyway, without further ado, Alicia.
Thank you, Gwen, for the introduction. I'm very excited to talk about my research. So let's kind of dive into some context. So my research is a branch of the MIRMOS project. For those unfamiliar, MIRMOS stands for Magellan Infrared Multi-Object Spectrograph. It's going to be an instrument implemented on the 6.5 Magellan telescope at Las Campanas Observatory in Chile. The goal of this spectrograph is to have both a wide field of view and multiple wavelengths. That way we're able to observe faint galaxies, the intergalactic mediums, and exoplanet atmospheres. It's also meant to be ran in a cryogenic environment, which is kind of important when considering how we want to mount the lenses of these. As you can see, there's like 6 of them, and they need to be held in a specific orientation, which is where we kind of start debating on what kind of mounting mechanism we want to use. So as of current, the MIRMOS team is debating between a bonded or optomechanical flexure design. My research specifically focuses on a bonded design. So the goal of my research was to verify the reliability of epoxy bonds via tensile and shear pull tests. So before I dive into that real quick, I kind of want to explain a bit more what exactly a bonded flexure is. So for my configuration specifically, it's only 3 components. So we have a glass lens right here, a flexure, and then there's a small epoxy pad that you can't really see in these 2 images. So what exactly are these things, just to kind of explain it a bit more. So epoxy is a sticky and strong plastic-based adhesive that has many different applications, ranging from marine applications to model rockets. And then a flexure is a piece of metal meant to hold the lenses in place. So I believe I have one of these here. I guess this is the 3D printed model. You can pass that around. So why or why not do we want to consider this? So some of the benefits that we've seen before in using a bonded flexure is we've seen successful use in the MOSFIRE project, which is kind of similar and also ran in a cryogenic environment. And it also has more degrees of freedom for shrinking. However, the one uncertainty that my research focuses on is whether or not the epoxy bonds are strong enough. So let's kind of go through the process that we went through this summer. The first step was getting started and obtaining some familiarity with SolidWorks interface. The second part was 3D modeling, like creating simple 3D models of each component. So that would be the epoxy pad, the flexure, and the lens itself. The next part was calculating some stress by hand, modeling the stresses of epoxy in the flexure, and creating and reviewing a finite element analysis. The next part was hypothesizing a failure value, adjusting the flexure so that it can have some bending stress, and then finding the epoxy to bead ratio. After that, we started getting some building done and working with the machine shop foreman, Vince, to fabricate some test fixture parts. And then the final part was assembling all of these fixtures and carrying out the pull test. So diving a bit more into what exactly is finite element analysis. So for our project specifically, we use SolidWorks' finite element analysis package to model and calculate the stresses. What you can kind of see here, it kind of gives you a bit of a heat map of the stresses, whereas the redder tints are where more stress is, and the bluer, cooler tints are where less stress is. So this actually helps us because we want to examine the behavior of the epoxy at numerous different weights. So we wanted to see it at failure, maximum weight it could hold, and if it could even hold the weight of the lenses. As you can kind of see in this photo, it tells us where the minimum stress is going to be experienced and where the most stress is going to be experienced. So that actually helps us out, because if we wanted to hold more weight, we'd add more epoxy onto that corner. And we know that when it is expected to fail, that's where it's going to have its failure at. In the end, we ended up calculating a safety factor of 100, which essentially means that it can hold about 100 times the weight of the lenses that we plan to use. And then the next part is the flexure progression. So the first design that we had was pretty simplistic. It was just a rectangular prism with a hole in it. It was 8 millimeters wide by 7 millimeters thick by 192 millimeters like long. We ended up deciding that that probably wouldn't be the best idea, as it kind of didn't have a lot of bending stress. And then on top of that, you can kind of see that hole failure. Unfortunately, I don't have a model of that one in. But from there, we decided to look more into a key-shaped design to kind of make sure there's more support in that area. And we also decided to go thinner, going from 7 millimeters to 2 millimeters to kind of make sure it has a bit of bending stress. And we shortened it to 50 millimeters to kind of be more consistent, I guess, with the size of the lenses. However, we decided in the end that probably wouldn't be the best to make sure we have some bending stress for when the lenses are expected to shrink and expand. So we decided to go with the third and final design, which was done in aluminum instead of 3D printed material like the two previous designs. So it kind of has the same shape. It's just a bit longer to kind of, like I said, add on that bending stress. And let's see, I have as well the previous design, I guess the second design for comparison. And then the next part was the epoxy testing. So we needed to figure out what ratio from RTV epoxy to the 0.0026 inch beads that we plan to use as spacers would work best. So we tested the following ratios of epoxy to beads, which were 95 to 5, 90 to 10, 85 to 15, and 80 to 20. In the end, only one of those stuck, which was our test number 1, the 95 to 5. Please be careful when, I guess, running your hands against these, but if you want to see how heavy, like how much it can hold against, that piece is available for you to look at. And this ended up being consistent with Mossfire's results, as you can see over here. They kind of got a ratio of 96 to 4 as theirs, which was pretty exciting considering we did it independently and ended up with the same results. And then the next part was our hypothesis and procedure of the pool test. So the pool test, I guess, to kind of explain in better detail what we're looking at here, the red mechanism, that's going to be this one, the back part, has like a circular cutout for the lens to sit kind of flush. And then the outer gray mechanism is a little like clamping mechanism to make sure we hold down the lens, but also has room for the flexure to kind of move as necessary, but not add stress. That'll be passed around as well. So from that, the first steps were placing the lens with the flexure into the clamping mechanism, clamping it down to the table with some C-clamps. And then we used a force gauge, which is approximately this. I can also pass that around. I'm sorry, go ahead. So we started with 5 pounds, which was the estimated weight of the lenses that we're going to use, and then increased in increments of 100 pounds until the epoxy detached from the lens. And then we did this for 2 different types of glasses, which were calcium fluoride and barium fluoride. And just reminding you of the hypothesis again, we hypothesized that the epoxy will fail at about 500 pounds. So these are the results from them. And what we kind of didn't expect necessarily so soon, at the very least, was we were only able to conduct one of the tests because the glass actually had broken before the epoxy had. So this one is the calcium fluoride and this one is the barium fluoride. I also have these in person as well to be passed around. They're covered in glass, not glass. They're covered in tape, so they should be safe to touch. But what exactly does this mean in terms of results and for Mossfire? Not Mossfire, Mirror. So this actually shows that our hypothesis was correct to an extent, as the epoxy held more stress than the material bond was able to hold. And just some sources of error that we encountered were we had to use expired A12 epoxy because our epoxy was backordered. We probably should have used some thicker lenses and gave it a little bit more cure time, but we were kind of on a time crunch. But for future implications, this means that epoxy bonded flexures are a viable and strong candidate for mounting the lenses moving forward. And we should look into doing some more testing, like in a cryogenic environment, using some fresh A12 and possibly using some thicker lenses. But yeah, that concludes my presentation. Any questions?
All right, very nice. Questions for Alicia?
Thank you.
So if you can go back to the slide where you have the different designs of the rectangle.
Oh, the flexure.
Yeah. So the difference in design 1 and 2, besides the shape, is that it's like the keyhole shaped. So is there like a physical reason to why the final design is key shaped rather than just a rectangular prism, or like having a hole not key shaped at the end?
So the main reason we did that was kind of make sure this had some extra supports, but we also still wanted to keep it a bit thin so that it would be able to bend as well. So we decided that a key shape was kind of the best compromise to make sure we have that support, but also keep the thinness. And also in the final design, like for the operational configuration, it's just going to be a rectangular like prism. So like we just kind of added that to make sure it had that stability for where we were going to pull.
Yeah, so you mentioned earlier kind of like this safety ratio. Can you go back to that slide and kind of like explain how you can potentially increase this like safety ratio?
Oh, the safety factor, I believe, is mentioned here. So different ways we could kind of increase that is adding some more epoxy into the corners, and I believe we have more flexures as well for the operational configuration. So we're still trying to decide the amount, but in the actual design, it's kind of going to be like tangential and connected at one point with the flexures. So we can add more like flexures onto that design to make sure it can hold more weight.
So I had a question on, you mentioned you have two different types of glass that you're looking at. So why are you looking at two different types? And also, is there any other type of glass you would want to look at?
So for the finalized design, I believe those are the two we're going to be using, barium fluoride and calcium fluoride. As far as other ones we'd want to look to, probably not at the moment, just because that's what we're using for this specific project.
Any other questions?
I was kind of wondering what adhesive was used for the two metal rectangles that were like stacked on top of each other.
Oh wait, I'm sorry.
What adhesive was used for the two like metallic rectangles that were stacked on top of each other?
For the two metallic pieces that we used for the epoxy testing, we used RTV, but in the final one, we ended up using A12. Any other questions?
All right, let's thank Alicia.